So good afternoon, everybody. I think the talk by Amir did a really nice job of providing some motivation for the challenge of urban flooding. So especially along the coastline, we see sea levels creeping higher and higher, and that means that the extreme sea levels are more likely to overtop seawalls and embankments and start causing nuisance flooding. Those same high tides, create backwater effects in estuaries and harbors, which can slow down runoff moving to the ocean or to the sea, and that can lead to increased flooding. We saw on the precipitation side these IDF curves, inundation frequency type curves, shifting to be sort of suggest more intense rainfall. And those curves are instrumental for design of urban drainage systems. Your typical engineer will look at those curves, identify a relevant time scale for that watershed, pull off the rainfall intensity, and that will dictate, the design levels, how much flow is going to be coming into the drainage network, and the level of capacity that you want to see in the drainage system. Those curves seem to be pointing in sort of a up and to the right, suggesting more intense rainfall for a given time scale, which is going to put more stress on the drainage network. On top of that issue, we have urban areas which are increasingly covered in sort of concrete and growing, leading to greater amounts of runoff as sort of urban areas grow. So there's a number of factors that point to, flood risk being one of those grand challenges we face going forward. I didn't even mention the fact that more and more people are moving into urban areas, and so we see increasing vulnerability, more to be impacted if it does flood. So if we, there's a clicking sound that I'm hearing. Does anyone know what that is? Did anyone else hear it? I guess maybe you can't speak. So I hope that clicking goes away, whatever it was. If you move to the first slide, I have a nice sort of photo of the beach here down at Crystal Cove, and here we are in Southern California, and I think it's easy to kind of be unaware that we do face significant flood risk in the area from the combination I just described, the rising seas, the intensification of the hydrologic cycle, increasing development in flood-prone areas. And the reality is that we have had a history of flooding as well. And if you move on to the next few slides, I have a few photographs of flooding that's occurred in the Orange County area and actually in Southern California generally over the past century or so. So here's a photograph of flooding in Laguna Beach in 1926. And the next slide shows the Crystal Cove area, 1937. Intense rainfall hits the coastal mountains. You see runoff, you see erosion of the banks. You see infrastructure like bridges that gets washed out. Moving to the next slide again, this is a photograph of Los Angeles in 1938. You can see that there's I think the river is flowing towards us in the upper left-hand corner, and so that river is coming down, trying to turn a corner, and we've learned over time that rivers don't like to turn corners very much. They tend to erode the banks, and then we see a big erosion of the banks. There were some concrete lined channels there that just got broken up and pushed away. We see a railroad crossing which was taken out by the floods. Floods are very damaging. It's among the most damaging and sort of life-threatening hazards we face in the world. Moving on, there's a photograph here of flooding in Anaheim, which is sort of central Orange County in 1938. And this is resulting from the Santa Ana River coming down, spreading out, inundating the urban areas around central Orange County. Next slide shows Newport Beach in January of 1983, which was one of the stronger El Nino years we've had on record. And that year there was a combination of factors which caused a lot of coastal flooding damage all along the California coastline. It was a coincidence of strong waves and high tides that led to water levels that were higher than all of the embankments around the harbor. In the upper right-hand side of this diagram, you can see water that's just at a level in the bay such that it just flows right over the top of the walkways around believe that's Balboa Peninsula. In the lower left-hand corner, you can also see part of Balboa Peninsula where the high tides from the sea and the bay have risen up over infrastructure and caused inundation of the land. So we've had flooding, significant flooding in the past from high sea levels, and we're thinking about what's going to happen as sea levels continue to rise and how infrastructure needs to adapt. And it's a major challenge facing the entire world, this issue of sort of sea level rise and coastal flooding. Just imagine another meter of water in this area and sort of how ill-prepared it is to kind of manage that right now. Move on to the next slide, Laguna Beach, another slide of El Nino flooding in the downtown area. This is just steps from the coastline where water had come up over the beach and ponded along Pacific Coast Highway. Significant ponding, you know, that's probably 20 to 30 centimeters of water ponded in the road there. And recently, since the 1980s, the city of Newport Beach spent a significant amount of money to try to upgrade its flood defenses, including higher seawalls. Yet there continue to be challenges. This is January 2005 when another sort of high tide combined with a storm event that brought in a storm surge of another 10 to 20 centimeters led to overtopping of the seawalls. Lower left-hand corner is a photograph of Balboa Island. If you were to visit the island, there's a walkway around the outside of the island and a little concrete seawall, and you can see there that the water heights are in 2005 were up to the top of that wall, and in fact came over the top of the wall. And again, you want to imagine a future where these seas are rising another, say, on average 3 millimeters a year for the next couple of decades and perhaps more. And so it's just increasingly likely that in any given year you're going to have a flooding event. And you can see the issue in the lower left-hand panel there is that you've got a business which is clearly is not necessarily having structural damage, but the arcade is not open for business. It's not able to attract customers. It's losing money, and that's an example of the sort of nuisance flooding impacts that we're starting to think about. If we move on to the next slide, you can see moving inland that intense rainfall creates flooding problems in our hillsides. Water moves down really fast off of the relatively steep mountains we have in this area, causing a lot of flooding and erosion. You can see the water is muddy brown. That roadways are easily sort of chewed up by the high velocities of the water running down through creeks. Moving on to the next slide is the city of Laguna Beach, which in December of 2010 experienced intense rainfall. In the upper left-hand corner, you'll see sort of churning water, and what you're seeing there is the main creek that comes down Laguna Canyon, and at the bottom of the canyon is the city center. And in the city center, the channel is sent underneath the city into a culvert, a box culvert, which is under capacity for the amount of runoff that occurs in that system. And so when there's enough rainfall, the water will come up over the road that we're looking at, and then run down the street and bring with it, water, not only water, but sediment. And if you look at the lower left-hand corner, you can see the sediment that's left behind on the roadway after the creek overflows and moves down through the city. It's again, not necessarily structurally damaging, but there's a impact to businesses. There's an operations and maintenance cost to clean that up afterwards, and these problems are ongoing. Another driver of flooding is waves. What we're seeing here in the next slide, showing Newport Beach in August of 2011, is a long period swell wave that came and overtopped, I believe that's Balboa Beach, or near Newport Beach, near Balboa Pier. And it's a combination of high tides, strong waves or high waves, long period waves that creates the opportunity for water to get up and over the beach and cause flooding of the peninsula. So with that as a context, we can see that the coastal areas of the world are facing multiple drivers of flooding. We have issues with local rainfall and runoff, causing flooding of streets. We have issues with the main channels, which can overtop and cause flooding. We have issues with extreme high tides that can overtop seawalls. We have issues with big waves that can overtop beaches. And commingled with the flood risk is erosion risk, which is a significant design consideration when infrastructure is put into place. Now, the word flood risk is used in a lot of different ways, and I'd like to define a little bit of different ways of thinking about flood risk. So, like a statistical definition of risk might be the probability of one or more exceedances of a threshold. An engineering definition of risk that's often used is the expected financial loss. So you think of like the assets that you have in place. So you have $1 million of property in a flood zone. The probability of that of an event, say, being 1%, and so then the risk would be the product of 1% and that value. So it's an economic metric. And in social science, there's a definition which I think is really helpful to think about, is that risk is the product of a hazard, such as a flood, with an exposure, which is people present, assets present, and then lastly, a vulnerability. So what can happen to those people if they are impacted? And this definition, I think, is not used enough in engineering, but it's really helpful for sort of having a more holistic view of how to manage flood risk, because we can think about the hazard and the exposure and the vulnerability separately and together. And historically, engineers have mainly focused on hazard from kind of an exposure perspective, and not so much from a vulnerability perspective. So with that as a background, I'd like to move on to the next slide, which is about the design of urban drainage in Southern California. So the first point is that the infrastructure, the drainage infrastructure, occurred in a time when runoff, sediment, and floodplains were viewed as hazards and not as resources. So imagine a developing area, ambitious, trying to grow, and dealing with floods. And the attitude was that engineers needed to create an environment where business could prosper, where people could farm, and hazards such as flooding could be controlled. It was a time when development opportunity was prioritized over habitat conservation. There's limited understanding of environmental science, including linkages between hydrology, water quality, and ecology. And these values motivated engineers to design channels that moved water to the sea in the most efficient way possible. So really, if you look at the urban drainage systems of Southern California, they are beautifully designed for the purpose of getting water as quickly as possible to the ocean. And the goal there was to prevent exposure, thinking about that idea of risk being the product of a hazard, exposure, and vulnerability. The idea was really to prevent exposure, and the engineering terminology that kind of stems from that is the whole idea of flood control. You'll see a lot of public works departments still use the terminology flood control, and it sort of suggests that we can control flooding and prevent exposure, which isn't always the case. So the main design principles is on the next slide that go into designing our channels. And the main design principle is based on the idea that we're trying to create channels that prioritize flow capacity. So we want channels that can move a lot of water. We want channels that are stable so they don't erode. And we want channels that have a minimal footprint, so there is opportunities to use the rest of the land for other purposes. That's the historical thinking behind the design of drainage systems. And the tool that goes into a lot of that is the Manning equation, which says that the volumetric flow rate Q is equal to 1 over a parameter n called the Manning coefficient, multiplied by the cross-sectional area of the channel, multiplied by the ratio of the cross-sectional area to the wetted perimeter, which we call the hydraulic radius, and multiplied by the slope of the channel. So the thinking then is if we want to have really efficient channels that move water to the sea, we need to sort of maximize hydraulic radius, maximize area, minimize resistance, and design so that the channel capacity is greater than the flood flows, and design so that the channel's resistance to erosion is greater than what the flood is going to possess. And if we move on to the next slide, you can see what you get when those design principles are put into action. We get rivers like the Santa Ana River, which is a trapezoidal channel lined with concrete. And move on to the next slide, another example of that sort of design philosophy, which is the Los Angeles River in LA. Again, an efficient system for water conveyance. Moving on, there's the Santiago Creek slide here, which is nearby campus in action. Again, this one's grass-lined. There's also a sort of riprap line channel here in Irvine that I'm showing in the bottom right. So that was kind of the engineering and construction that went into the drainage system that we have today. And there have been some negative feedback loops that we've also had to manage. One is increased peak flows. So as a result of greater imperviousness and less channel storage, what happens is that the peak flows from floods are greater today than they would have been under a pre-development condition. Another negative feedback loop is a levee effect. The idea here is that as we develop levees and control channels that create the impression of protection, then that tends to promote more development in high hazard areas. People are under the perception that they're protected, and so you tend to have greater vulnerabilities after the construction of civil infrastructure. And a third negative feedback loop is degraded water quality and stream ecology, which is a major focus of a PIRE project, a Partner for International Research and Education between UC Irvine, UC San Diego, UCLA, and our colleagues at the University of Melbourne and Monash University in Australia. And a focus there has been on this symptom or condition that urban streams are in, which we call the urban stream syndrome. And the next slide gives some overview, which summarizes some of the symptoms of the urban stream syndrome. So top panel shows channels with high flow velocities, degraded channel morphology, poor water quality, unhealthy levels of sort of stream ecology. So those are kind of what we see in urban rivers around the world. The hydrologic drivers are in the next set of images, including imperviousness from concrete and roofs, formal drainage systems that take water, quickly move it into sewers, quickly move it into storm channels, and quickly move it as fast as possible. Stream modification, sediment, and even imported water, which changes some of the base flow that we see in the system. But in response to these symptoms, there is now a movement underway to try to reverse these problems, doing things like adding biofilters, soft surfaces, permeable pavement, green roofs, rain tanks. There's a number of different measures that are being proposed and actually being implemented to try to manage these problems. And they're designed, moving on to the next slide, to reverse the impacts of urbanization, increasing storage, decreasing velocity, increasing infiltration, increasing contact with sediment vegetation. And as we do this, I think it's helpful to kind of look a little bit at the natural systems of Southern California to see whether there's some features that can inspire our additional design of these what we call low impact development measures. So the next slide shows a picture of the Santa Clara River, which I like to use as a good example of a natural floodplain in Southern California because it's very limited development in the floodplain. And I tend to think that some of our rivers like the Los Angeles River and the Santa Ana River might have looked something like this had they not been developed. And what we see is a system that's wide, it's flat, it's hard to even see a channel. We see some little bit of water here and there, we see sediment, we see scrub vegetation. And so in the absence of development, this is kind of what nature did with channels in Southern California. Another good example is the Tijuana River, which is just north of the Mexican border. And here we've seen quite a bit of development for agriculture, but it's since been gone into kind of more of a state of where it's not being used much for agriculture. It's mainly used for, there's some ranching going on, there's some horse breeding. But you see a system that's wide, relatively flat, vegetated, and another sort of site condition in Southern California, shot from the Mojave Desert, where we see an alluvial fan coming out of the mountains and spreading out onto a desert floor. And here I think is a nice example to think about and to keep in mind in Southern California, because much of our development is on alluvial fans. And when we have an alluvial fan, you have very little, the channel basically can go just about any different direction down the slope. It may go one way one year, may change course another year. That makes it really difficult to mimic sort of create an engineered system that mimics a natural system because of the way that the flow just wants to take a different path each time. And if you're trying to develop, imagine that this alluvial fan that we're looking at here was once the floodplain between say the San Gabriel Mountains and the sea, where Los Angeles is. And imagine trying to lay out a city when you had a river system that wanted to go all over the place like this. So clearly we had to kind of strike some balance between managing waterways and supporting development in industries. And it's just a challenging thing to try to mimic natural processes in a system like this. If we move on to the next slide, you can see a photo of, or depiction of the floodplain of the Santa Ana River, which unfortunately is a little grainy, but gives you the idea that naturally the Santa Ana River wanted to flow really wide and broad over much of Orange County and southern Los Angeles County. And this motivated the channel systems we have today, which are these narrow concrete lined channels to move water quickly to the sea so it doesn't spread out and impact the area. So just to contrast drainage systems right now, this next slide shows contrast between undeveloped areas and developed areas. In undeveloped areas, we see wide channels, we see shallow flow, we see vegetation, sediment as a resource that moves with the fluid. In developed areas, we see narrow channels, we see deep flow, we see unvegetated systems, and sediment really poses a hazard. When sediment gets into an engineered channel, it reduces cross-sectional area, it promotes vegetation growth, which increases the resistance, and so it decreases the capacity of the channel. So there's fundamentally a conflict between managing flood risk and trying to promote other benefits like water quality, habitat, and so on. So where are we now? Well, the good news is that we have a drainage infrastructure. This is the next slide here. Drainage infrastructure, which is doing a really good job of managing flood risk overall. I mean, we have levels of protection in major rivers and in local collection systems. It's really quite good. I mean, I think we do have problems with local flooding. Along the coast, we have some serious issues to think about. But overall, across the region, flood risk is managed somewhat reasonably. But the problem is we've had all these other adverse consequences. So we now have major challenges managing sediment. Los Angeles County alone spends around $100 million a year to manage sediment in debris basins. So the channel system isn't designed to accommodate sediment, so instead the channel system collects sediment in debris basins, and then they have trucks come in, dig up the sediment, and truck to landfills. So that's a very costly, and it's also looking at sediment as a waste product and not as a resource. We also have major challenges managing water quality. We have high levels of nutrients, pathogens, metals, organics, etc. And this leads to really costly monitoring and control programs. We've seen the loss and degradation of habitat and ecology of the system, and the negative social impacts that come from communities not having access to a stream nearby where they can go for a walk and be in the shade and observe the environment. We also face a really challenging institutional system where ownership issues are complex, government oversight is complex, agency oversight is complex. So it's really difficult to even get involved and start making changes because of the complexity of our institutions. And we face limited funding. I mean, the amount of resources we've invested in our drainage infrastructure are massive. And to think that we could somehow, restructure them, it's a long road ahead. But the good news is, in my mind, is that we have increasing demand for water security, and that's promoting interest in things like stormwater harvesting and groundwater recharge, and also social benefits. And we're seeing communities that have been designed to sort of strike a different balance between the environmental around them and the development within it, and those are attractive. Those lead to high property values, and I think that puts more pressure on other areas to try to recover some of the environmental qualities that were lost when channels were put into concrete lined channels, as an example. So Momentum is building some examples up in Los Angeles. There's something called the Sun Valley Watershed Project, where they're working on redeveloping an area to do things like manage stormwater runoff, increase water conservation, increase recreational opportunities, increase wildlife habitat, reduce stormwater pollution, doing things like installing rain barrels and biofilters and wetlands and so forth. Moving on to the next slide, the City of Los Angeles has an ambitious plan to try to revitalize the Los Angeles River. And this is a depiction here of what an architect visionary thinks that they can accomplish in the Los Angeles River. So these are great goals to set. How we achieve them is another matter, but there's sort of interest and momentum in I think a positive direction. And right here in Orange County, we have an environment which is really promoting regulations that are requiring implementation of low-impact development and new as we build out, and encouraging implementation of LID in existing residential areas, and we're going to hear shortly from John Ping from Orange County Public Works about the things that are activities here in Orange County that are trying to address this issue. So I'll close just with something I think is a major challenge, but also a major opportunity. And if there's engineering students out there that are thinking about future careers, I mean, the upper left-hand corner here shows what we have today in much of the Southern California, which is these concrete-lined channels moving water to the sea. And the bottom right shows someone's vision for what we could accomplish if we were to sort of rethink the way our drainage infrastructure is laid out. Getting from the upper left-hand corner to the bottom right-hand corner is not trivial. It's going to require a lot of money. It's going to require some bright people. It's going to require some science and some engineering practices that are different from what we have today. But I think it's an exciting area for young people to get involved and to move ahead. So with that, I will take questions.
Yeah, Brett, it's Tim Fletcher here. I'm inspired by that last slide. Well, not the questions slide, but the one before that. You know, those two pictures, as you say, they really, you know, I think they're simple, but there's actually a lot of work to get from that top left to the bottom right. And you've described quite well some of the local initiatives that are occurring at both, I'll call it the kind of river end, where you're actually thinking about doing works like this in the river, but also in the, you know, up in the catchment where the problem is really coming from. And so I suppose I'm wanting a little bit more information about that. How much do you, or to what extent do you think the policymakers are understanding the link between what needs to be done kind of at the source, you know, with the rain barrels and the rain gardens and all of those kind of things, and in order to achieve something like that photo in the bottom right, because ultimately the feasibility of that vision in the bottom right really depends on, to a large extent, what's done in the catchment. And do you think there's an explicit understanding of that and a commitment, therefore, to slowly retrofit the urban fabric to therefore allow something like the bottom right to exist?
Well, yeah, I'm glad, excellent point. You know, and what I'll say is that there's a wide range of people with different levels of understanding. So it's hard to say this is the level of understanding in the system. I think the fact that there's changing policies in places like Orange County to promote the low-impact development at the local level, I think reflects the understanding that that's really important. That we can't do the stream restoration until we, you know, reduce the stress that's being put under from the runoff from the local catchments. So, so I would say that but I think that I'm not sure. I don't think the level of understanding between what we can do in the drainage network is really developed yet. I think that there's a lot of skepticism from people I've talked to that we can ever do anything with the amount of land that we have. You know, that there's been some studies that have kind of looked at, like ours, that have looked at what, you know, different stormwater control measures can do to the peaks of floods, in terms of reducing the peaks to the point where we can sort of, you know, maybe relax the expectation of the channel, and the feeling is that, you know, maybe for the more frequent events, the 2, the 5, the 10, the 20-year event, that yeah, we can do something there, but trying to do something with the 100-year event for which the channel is designed is thinking is it's going to be tough to do that. Perhaps though there's roles to be played for like an intermediate scale. I mean, John Ping's going to talk about a basin, I think, that Orange County is working on to kind of have some significant storage, you know, in the middle of the watershed, and perhaps with the right mix of reservoirs, and there's possibility to have an impact. But I think that overall, I think there's a lot of skepticism about what can be done in the sort of try to restore the major drainage systems. But I don't know, maybe John Payne could comment on that as well.
All right, I'm gonna actually talk a little bit about in that direction. I think you and Amir really, did a very good introduction. It set the tone for my presentation as well.
Okay, well, I guess on that note, we can go ahead and move over to Dr. John Ping with Orange County Public Works, who will be talking about Orange County initiatives for stormwater capture and infiltration. So you can take it away.
So for the presenters, I'm gonna actually share my screen, and for the audiences, you guys can just march forward with the slides. So let's see. Amir and Brett really did a very good introduction on the extreme event and urban drainage issues, and I'm actually gonna talk about solutions, at least from the Orange County perspective. So next slide. I actually have 4 main topics. Since the